Dear students, in this episode of complex numbers, I am going to talk about de Moivre's theorem. De Moivre's theorem connects trigonometry and complex numbers. By using de Moivre's theorem, we can obtain trigonometry functions for multiple angles. It also helps to connect powers of trigonometry functions and trigonometric angles. Before watching this episode of complex number, I request you to watch episode 1 to episode 6 for thorough understanding. So let us start today's topic, de Moivre's theorem of complex numbers. Suppose n is a real number, any real number, and suppose we are having cos theta plus I sin theta whole raised to n. Then the expansion of cos theta plus I sin theta raised to n is equals to cos n theta plus I sin n theta. Example cos theta plus I sin theta square equals to cos 2 theta plus I sin 2 theta. In place of n, we can select any real number. Example, cos theta plus I sin theta. Suppose I select 5 here. You say, why only 5? You want to select 7. Okay, you select 7. Somebody else will say, no sir, 7 bhi nahi, 5 bhi nahi. Let us take 11. Okay, 11. Whatever the number you want to select, you can select here. So cos theta plus I sin theta whole raised to 11 equals to cos 11 theta plus I sin 11 theta. So by using de Moivre's theorem, we can easily expand the given complex number written in terms of polar form. This is the polar form of the complex number, and you want to expand the polar form of the complex number to any given index, easily you can get the answer. So this is what the best use of the de Moivre's theorem. Even you can select the negative numbers like cos theta I sin theta raised to minus 4. So you can select the negative number as well as, so that is equals to cos of minus 4 theta plus I sin of minus 4 theta. That is nothing but equals to cos of 4 theta minus I sin of 4 theta. Why? Cos of minus k equals to plus cos k. You might be knowing from trigonometry, and sin of minus k equals to minus sin k. These are the two outcomings from the trigonometric basic. Cos of negative angle equals to positive and sin of negative angle equals to negative. This is the property, this is the identity taken from the trigonometry. So this is the way you can expand any polar form of the given complex number in a given positive or negative index. Suppose z equals to cos theta plus I sin theta and 1 upon z equals to question mark. So 1 upon z is nothing but z raised to minus 1. Since z equals to cos theta plus I sin theta, therefore z raised to minus 1 equals to cos theta plus I sin theta whole raised to minus 1. That is equals to cos of minus theta plus I sin of minus theta. So that is equal, cos of minus theta is plus cos theta, sin of minus theta is minus sin theta. Therefore cos theta minus I sin theta, that is equals to 1 upon z. Thus by using de Moivre's theorem, if you know the value of z, easily you can find out the value of 1 upon z as well as. The use of de Moivre's theorem can be extended to solve the complicated problem of trigonometry. Wherever the complex number and trigonometries are involved, we can easily simplify by using de Moivre's theorem. To understand this, let us take few examples. Suppose we got the two complex number z1 equals to cos 2 theta plus I sin 2 theta and z2 equals to cos 3 theta plus I sin 3 theta. Then you require to find out z1 into z2 equals to how much. So z1 equals to cos 2 theta plus I sin 2 theta. We know that de Moivre's theorem, cos n theta plus I sin n theta equals to cos theta plus I sin theta whole raised to n. It is a formula. By using this formula, I can just write this cos 2 theta plus I sin 2 theta can be written as cos theta plus I sin theta whole square. And z2 equals to what? Cos 3 theta plus I sin 3 theta. By using the same formula, we can write it cos theta plus I sin theta and whole raised to 3. That means the cos 2 theta I sin 2 theta, the 2 is shifted to the index. Similarly, in case of cos 3 theta plus I sin 3 theta, 3 is shifted to the power, that is a cos theta plus I sin theta whole raised to 3. Now z1 into z2 equals to cos theta plus I sin theta whole square. This is z1 value and z2 value is cos theta plus I sin theta whole cube. Now the bases are equal here, therefore we can add the powers, that is cos theta I sin theta whole raised to 2 plus 3. So that is equals to cos theta plus I sin theta whole raised to 5. So this is equals to cos 5 theta plus I sin 5 theta. Therefore z1 into z2 equals to cos 5 theta plus I sin 5 theta. Now if there is a minus in between, then how to multiply the two complex number? Suppose cos 2 theta minus sin 2 theta, z1 equals to cos 2 theta minus I sin 2 theta, and cos z2 equals to cos 3 theta minus I sin 3 theta. Then how to find out z1 into z2? We know that formula, cos n theta minus I sin n theta equals to cos theta plus I sin theta raised to minus n. Therefore z1 equals to cos 2 theta minus I sin 2 theta. This can be written as cos theta plus I sin theta whole raised to minus 2, and z2 equals to cos 3 theta minus I sin 3 theta equals to cos theta plus I sin theta whole raised to minus 3. z1 into z2 equals to cos theta plus I sin theta whole raised to minus 2 multiplied by cos theta plus I sin theta whole raised to minus 3, that is equals to cos theta plus I sin theta. The bases are equal, so we can add the powers. So cos theta plus I sin theta, so that is equals to cos theta plus I sin theta whole raised to minus 5. So z1 into z2 equals to cos of minus 5 theta plus I sin of minus 5 theta. So that is equals to cos 5 theta minus I sin 5 theta. That is the result of z1 into z2. Thus, we have seen that even though there is a plus or minus, we can easily use De Moivre's theorem. Now let us have one more example to find Z1 upon Z2. If Z1 and Z2 are given, by using the De Moivre's theorem, we can easily simplify Z1 upon Z2. Suppose Z1 equals to cos 2 theta plus I sin 2 theta and Z2 equals to cos 5 theta plus I sin 5 theta. Find the value of Z1 upon Z2. So Z1 equals to cos 2 theta plus I sin 2 theta equals to cos theta plus I sin theta whole raised to 2 by using De Moivre's theorem. Now Z2 equals to cos 5 theta plus I sin 5 theta, that is equals to cos theta plus I sin theta whole raised to 5. Now Z1 upon Z2 equals to cos theta plus I sin theta whole raised to 2 upon cos theta plus I sin theta whole raised to 5. Now both the bases are same, so we can use this formula a raised to m upon a raised to n equals to a raised to m minus n. So this is equivalent to cos theta plus I sin theta whole raised to 2 minus 5, that is equals to cos theta plus I sin theta whole raised to minus 3. Therefore, Z1 upon Z2 equals to cos of minus 3 theta plus I sin of minus 3 theta. This is by using the De Moivre's theorem, and that is a cos 3 theta minus I sin 3 theta. This is nothing but Z1 upon Z2. In this way, by using De Moivre's theorem, we can easily divide the complex number given in polar form and easily simplified to a very suitable and very simplified form. Let us take some more complicated problem on the basis of De Moivre's theorem. Prove that sin beta plus I cos beta raised to n equals to cos pi by 2 minus beta n plus I sin pi by 2 minus beta multiplied by n. Now, first of all, we need to convert this sin beta into some like a cos term, and this cos beta has to be converted in terms of sin. Then only we can prove the RHS, and De Moivre's theorem is applicable if here is a cos and here is a sin. So first of all, we need to convert these trigonometry functions. Sin has to be converted into cos and cos has to be converted into sin. Then only we can get the RHS value. From basic trigonometry, sin beta can be written as cos of pi by 2 minus beta, and cos beta can be written as sin of pi by 2 minus beta. Therefore, LHS equals to sin beta I cos beta whole raised to n can be written as cos pi by 2 minus beta plus I sin of pi by 2 minus beta whole raised to n equals to cos pi by 2 minus beta into n plus I sin pi by 2 minus beta into n, that is nothing but equals to RHS. Therefore LHS equals to RHS verified.